Okay, macam selalu. Okay, to study the electrochemical behavior. Okay, so oxidation and reaction of substrate. Substrate here is the working electrode. Okay, so the working electrode problem. Okay, substrate, working electrode in bulk katanya boleh je create new room. Oh, macam tadi. I continue je lah. Okay, something in the bulk solution containing active species. Okay, detection of reaction intermediates. Okay, so first you will know the redox. Okay, reaction on the working electrode. For example, working is mercury. So you will know the limit on the negative side and positive side. Okay, in bulk solution containing active species. For example, active species, you are going to determine cadmium. Okay, you will plot the polarigram for DME. But for CV, you will know the process of reduction as well as oxidation on the substrate. Substrate could be mercury, platinum, carbon, or whatever conducting material. Okay, so then you also can observe the follow-up reaction. Okay, I'm going to talk this more detail at the end of this part. Okay, cyclic voltammetry. So to identify the electrochemical reaction reversibility, okay, either the process is reversible, okay, berbalik, or quasi-reversible. Quasi is it's similar, it looks like reversible, but the characteristic of the the voltammogram is not reversible. Okay, I'm going to talk this later on. And irreversible, okay, not reversible. Okay, I will show you the type of cyclic voltammogram which represent reversible, quasi-reversible, as well as irreversible. Next, to indicate the anodic limit. So you can identify on the positive direction, the anodic limit is the positive potential, the oxygen evolution, and the cathodic direction, hydrogen evolution. Okay, next, to determine the surface area, you also can use CV in order to determine the surface area of the material. And also you can study the mechanism of material, okay, kinetically, okay, control or mixed control or diffusion control. Okay, so this is example of the measurement, okay, the setup for the potential state. Okay, it contains 3 electrodes. This is counter, the black one. The middle is the reference. The red is the working electrode. So in this solution, the blue color contains the target species, electroactive species, to be determined. Okay, so this is the the potential state. Okay, so it will convert the signal into this plot. So this is called cyclic voltammogram. Okay, next. Okay, so this example of the limit. Okay, so this color blue is the limit on different material. Okay, for example, this is on mercury, so this is on gold, for example. So if you can compare these two, the limit on mercury is more overpotential, large overpotential for oxygen evolution. This side, so this is, for example, on gold, this is on mercury. So mercury is still more large of potential for this side is hydrogen. Again, don't get confused. Okay, I have shown on each voltammogram or polarigram. Okay, the convention for floating convention for each voltammogram. For example, this is, you can see here, positive direction. So if you see, any question, Loliana?
No.
Okay, so this is positive. Ada order masuk ke? Okay, so this is positive direction. So when you see the potential is going more positive, so this is the oxidation. So this is positive current, this is negative, so this is UK because oxidation is on the right, reduction on the left. This is UK convention. Okay, so this is the limit on different material. On the positive direction, the limit is oxygen evolution. A lot of bubble of oxygen evolve or form on the either gold or mercury. Okay, so this is the limit. So where this act, this side, this direction, this working electrode act as anode. Anode is oxidation. So, but for this direction, negative direction, this negative potential, more going on the left hand side is the increase of potential in negative sign. So this is reduction. Okay. So the limit for this, for example, gold, this is hydrogen evolution. So the working electrode act as cathode because this is reduction. So this is the clear range, potential window range. You can do analysis to plot the cyclic voltammogram, this cycle. Okay. If you scan above this line, so you will not see the cycle because you will only see the increase of current because the interaction from the evolution of oxygen this side and this evolution of hydrogen. So that's why you must identify the potential window range before doing your experiment. Okay, I hope you understand that. Okay, so this is the value over potential. This is the middle E half. Okay, so this is the over potential before the evolution of hydrogen. So start at 0.4, then it's around 1. Yeah, so the over potential before the evolution of oxygen is 0.6 volts. Here the over potential from 0.4 to before the starting the formation of hydrogen is about negative 1.1. Okay. Okay, so this is the value. Okay, the large over potential for hydrogen evolution on the left and also over potential on the right for hydrogen evolution. Okay, oxygen. Sorry. Okay, look at this. Okay, this is very common. If you are electrochemist, you in order to check, calibrate your instrument potential state, whether the potential state is okay or not, you should do this scan, cyclic voltammetry. You will plot cyclic voltammogram of this ferrum 3 complex form, okay, ferric cyanide ion will reduce. If involve only one electron transfer, will reduce to ferrocyanide. Okay, so the E half or is half wave or half potential is the between this. Okay, located here. So if you check from the literature, this is the value for these two couple, ferrum 3 and ferrum 2, 0.36 volt. Okay, so this, what are the parameters can be drawn or can be accepted from the cyclic voltammogram are the EPA. Okay, this is the UK, UK convention because this is oxidation. Okay, so you can get the EPA. So this is E, so this is I. Okay, The y-axis is current, the x-axis is potential. So you can see this is the peak, the highest current. So you take this at x-axis is the EPA, the potential for peak anodic peak. So this is IPA. This is I. Okay, current. This is current. This is potential. So on the reverse stand, okay, the reduction process. Okay, so this is E, not I. EPC. EPC. Here is EPC because this is the peak of cathodic. So this is E. And this is I. IPC. Okay, so there are four parameters from this voltammogram can be determined. EPA, peak for anodic process, peak for cathodic, as well as the current. Okay, anodic peak and cathodic peak. Okay, so I hope you understand from the cycle voltammogram for reversible, you can determine four parameters. Okay, all these values can be readily obtained from the cycle voltammogram. Okay, measuring eyepiece, the peak involve the extrapolation of the baseline current. Okay, so this is the baseline current. Okay, so from here you can measure the IPA. From here, this is the baseline current. So this is the peak of the current. Okay, so this is the gap between the baseline current and the peak. We call it the peak current for cathode on the bottom side. On the top side is the anode. Okay, look at this. Okay, this is waveform for T time versus E. Okay, waveform. So this is waveform for I versus E. Okay, this is voltammogram. So this is waveform for time versus E. Okay, so this is when you see this is on the negative direction. On the right is negative, so this is US convention. Okay, this side is positive direction. So it can for this to plot this voltammogram, it can this is the starting here, okay, at 0.8. Start at V1 is 0.8 volt and to negative 0.2 volt. Okay, then it back to 0.8. Okay, start here and then the project peak and then the switching potential here and reverse. This is the opposite peak and stop at the initial voltage. So you will plot this. If you plot time versus E, you will get this shape. Okay, this is 0.8 volt. Okay, you move to negative 0.2 and back to positive 0.8 volt. Okay, so you plot time versus E, this diagram will be plotted. If I versus E, you will get a cycle. So this is called cyclic voltammogram. So actually each point, okay, start at A until K. Okay, you can see here A. Okay, similar to this, only the axis is different. Okay, so this is A, so this is A. Okay, so from A to B, okay, so there is no reaction. Okay, but at A actually the oxidation of water. So this is oxidation of water. Okay, so here water will oxidize to oxygen if you further upstand to more positive, but that is not shown here. Okay, so then it moves to more negative value here, to more negative direction. There's nothing happen here because the current is zero. Then at B, suddenly, okay, B to H. Okay, this line or this curve from B to H represent reduction process. Okay, because this negative direction is reduction. So the maximum located at D. Okay, the maximum reduction process is at the peak of the voltammogram. This is the switching potential back to the initial. So from H, okay, to uh, K is the opposite reaction, which is oxidation. So again, it's reversible reaction, so it also has this peak. So this peak is the maximum oxidation process of that reaction. Okay, so I hope you understand. If you don't understand, just ask me. Okay, now we look at the cyclic reversibility, CV reversibility. Okay, it has reversibility has three terms: reversible, quasi-reversible, irreversible. Okay, so in order to confirm whether the reaction, the redox process reversible or not, so for reversible, the EP is between EPC and EPA, the separation is about. So to check the reversibility of the reaction, okay, what is the reaction? Oxidation and reduction. Whether they are reversible or quasi-reversible or irreversible. Okay, how do you know that the reaction is reversible? By looking at the voltammogram, cyclic voltammogram. So you look at this, the black uh, voltammogram, black color. Okay, that is called reversible. Why reversible? The separation between EP, let's say this is EPC. Okay, if the US convention EPC, downward is EPA. Okay, so the separation between E here is EPA, this is EPC. Separation gap between these two peak potential for one electron transfer is about 59.2 millivolt. This is volt. Okay, 59.2 volt. Around that 60 millivolt, we consider that reaction is reversible. Reversible means, for example, ferrum 3 reduced to ferrum 2. Okay, so it happened on the working electrode. Okay, so from ferrum 3 to ferrum 2, will accept one electron. Okay, so whatever was reduced, this is reduced, 3 to 2 reduce, reduction. 2 to 4, 2 to 3 is oxidation, reverse. So what if this is 1 molar, then they produce 1 molar, ferrum 2. Then ferrum 2 back to ferrum 3, 1 molar also. So it's called reversible. Nothing happened. There's no intermediate form or new product form from this reduction. All convert, all ferrum 3 was converted to ferrum 2 and ferrum 2 oxidized back to ferrum 3. That is called reversible. 100% the formation of ferrum 2 back to ferrum 3. But for irreversible, okay, it is not reversible, so it can appear like this. You can see the peak. Then when you ask the system to reverse, there is no peak at the bottom, okay, because it already formed product, permanent product. For example, copper, okay, reduced to copper on the surface of working electrode. It's permanently formed, deposited on the working electrode. Then when you cycle back, there is no peak. Okay, it represent the irreversible reaction because it is not daily. There is no the ratio is not 1. Okay, for quasi-reversible, it looks like reversible, but the characteristic, if you calculate the amount is, for example, the separation between EPC and EPA is very wide. Not 60 millivolt or 59.2 millivolt, but more, probably 150 millivolt, the separation between EPC and EPA. So this shows that it is quasi reversible. It looks like reversible, the shape, but it is not reversible. Do you understand that? I hope you understand. Okay, first reversible. Okay, I've told you the separation between these EPAC and EPA is about 60 for 1 electron transfer reaction. Okay, then V, the scan rate, the V is independent of no, the EPC or EP here, the peak here, EPA, EPC and EPA is not dependent on scan rate. If you scan rate is you scanning rate, okay, you can use the lowest or the smallest scan rate millivolt per second. You can increase to 50 millivolt. Okay, you can increase to 500 millivolt. Okay, so this one will show the same pattern of reversible reaction. It is independent of scan rate. Okay, if it is independent, so you will see this direction and it moves. EPC or EPA move to according to the increase of scan rate. Let's say this one is 10 times. Okay, so it should move to 10 magnitude of potential. But for reversible, if you change it 10 times of scan rate, it's still at the same potential. Okay, that is characteristic to be reversible reaction. Okay, so you can check whether the reaction is reversible by calculating the Homer reduction potential. Okay, the separation between EPA and EPC. This is the formula. You find the EPA, the peak for anodic, peak for cathodic, plus, and then you divide with by 2, so you can get the Homer potential. Okay, the middle potential. Okay, let's say you have this. This is EPC. This is EPA. Let's say this is 0.1 volt. So this is, let's say, 0.4. This is 0.35 volt. Okay. So you get this 0.4 plus 0.35 divided by 2. You will get 0.3 the any answer in pakai calculator? For 0.375. Okay, 75 volt. Okay, so this is the formal potential for that reaction. Okay, so you should check this first. Okay, the formal potential for reversible reaction. Get this value and plus this value divide by 2. So the middle here, somewhere here, this value E Homer. It at equilibrium. Either the process wants to oxidize or reduce at the middle. So the number of electron transfer in reversible reaction can be determined from this, the gap between EPC and EPA. Okay, so then this is 1, this is the formula. So if the N is 1, so you should get 59.2 millivolt or 0.059 volt. Okay, that is reversible reaction. Beside that, it is similar. The ratio, okay, this is I, this axis as I current. So this is cathodic, so this is IPC. So here, this is IPC, okay, from the baseline to the top peak, this is IPC. You should measure, okay, the length of this from 0 to the peak, as well as this the bottom peak. Okay, so this is IPA. So if that is reversible, IPC, this value, let's say positive 1 ampere, this also negative 1 ampere. 1 over 1, it should get 1, meaning that what is reduced will oxidize back to the original species. Okay, the ratio reduction, the amount of reduced species must equal to the amount of oxidized species. That is reversible. Then again, this I have mentioned is not dependent of scan rate. Okay, the value of either EPA or EPC, as I said earlier, is not dependent on the scan rate. If you scan very fast, if it is dependent, it will drag to a higher potential. But if it is reversible, if you use faster scan rate, it will produce at about the same potential. Okay, it's independent of scan rate. Okay, there is one equation, we call it random subject. Okay, in your lab assignment number 5, okay, you should use this formula in order to determine C. Okay, the purpose, the task is to find the concentration of unknown. Okay, so the peak current, okay, you have several scan rate. If you manage to do the experiment but you don't, okay, so you can produce several CV, okay, like this. So you will determine IP, for example, IPA or IPC at different scan rate. So this is scan rate, this is peak. Okay, you will plot, okay, the square root of scan rate and IP, either IPA or IPC. You will get straight line. Okay, so then you will measure slope. It is the slope. Okay, this is for lab assignment 5. Okay, this slope is this one you bring here. Okay, IP versus square root of V. Okay, you remove this. So this value is the slope of the plot. Okay, the slope, you get this value, you bring it here. So you can determine C. Provided that you know this is 1, N is 1, electron stoichiometry. A is the electrode area. Electrode area is given. In the lab report, in the lab assignment, I have given the size of the gold electrode. Okay, I think it's about 0.078 cm square. Okay, so you know A, the size of the gold electron as working. Okay, D, diffusion of the ion. Okay, ferrocyanide ion. Okay, it's also given, I think. So what is still missing is C. Okay, you can identify unknown. This is quantitative analysis. You are quantify something. For example, ferrocyanide. What is the unknown concentration in the test solution? Okay, by plotting voltammogram, you can plot this IP versus square root of scan rate. So you will use random searching equation. You will find the concentration of unknown. Okay, a plot of IP versus C should give a straight line with an intercept of 0. Okay, large deviation. Okay, you also can plot IP, okay, versus, okay, there are two parts in that lab. One is different scan rate, okay, different scan rate. One more is different concentration, okay, different C. Okay, you have two set of data. If you look at the lab assignment, okay, so you are going to submit it, the lab assignment. So there are two parts. Part A, I think, is about different concentration. They are very concentration. Okay, so then it's different scan rate. Okay, so first, if you plot IPC versus C is 2 millimole to 10 millimole. Okay, so this is, you can get IP. Okay, the IP is this one. Okay, the increase of current. Okay, you should plot this, so you will get different set of IP, IPA or IPC. So you will plot IP versus C, you should get straight line. Okay, so large deviation from zero, this is zero. If there is large deviation, it start here. So this deviation is not intercept at zero, but here. So this deviation can assume as absorption. The species absorb on the working electrode. Then IP versus square root of scan rate should give this plot, should give a straight line. So the slope of which can be used to determine diffusion and a unknown. Okay, for this slope, you are going to determine this, sorry, D. Okay, you are calculating this D. Your target is to find diffusion coefficient. C is given 4 millimole. Sorry. Okay, for this, you are going to determine D. For this slope, I versus C, you are going to determine unknown concentration. I hope you can follow if you look at the lab assignment. Okay, so you have two set of experiment. One is different concentration, one is different scan rate. You will plot two series set of voltammogram, cyclic voltammogram. Okay, one various concentration, another one various scan rate. So you will plot I versus C for the first one. So you will find unknown concentration. Okay, there is one sample is unknown. You do not know the concentration, but the rest you know 2, 4, 8, 6, 8, 10 millimole. But one sample is unknown. So you will determine the concentration of C. Okay. Once you know the current peak, you can determine from the plot, you can determine C. What is unknown here? It should be in between from 2 to 10. Okay, probably 5, 4, 6. It's not out of the line. Okay, for the second part, okay, you vary the scan rate. This one, you vary the scan rate using random searching. You are asked to determine diffusion coefficient D, capital letter D. Okay, try. Plot I, PA or IPC versus square root. Then you will get straight line. Find the slope. From the slope, you include added into this equation. What is still missing is the diffusion coefficient. Okay, please submit your lab assignment. Okay, next, that one about, okay, reversible. Now we come to irreversible. Okay, as I said earlier, this is example of irreversible because there is no return peak. Okay, reverse peak. Okay, for example, this is positive, positive current. So this is negative direction, voltage. Okay, this is current. This is E, voltage. Negative direction, positive current. So this is reduction process for US convention. I hope you understand that. This is positive, this direction, potential. Current here, negative, downward. Okay, look at this. The voltammogram above shows the reaction of species A. For example, A will reduce to B. Okay, product B on the electron. Okay, so but on the reverse scan, on positive direction, no oxidation of B to form A, back to A. So B is permanently formed or deposited. Okay, so the absence of oxidation peak. This is peak for reduction peak. Reduction peak. So there is no oxidation peak. So this is called irreversible reaction. It is not reversible. Irreversible. Okay, another example of irreversible. You can produce peak, but small peak. Okay, the ratio for IPC, for example, and IPA is not 1. Okay, if you divide IPC and IPA is not 1. Okay, one is very large, one is small. So the ratio current between anodic and cathodic is not 1. So that is also irreversible. Okay, as well as the separation, very wide. Okay, it's not 60 for one electron transfer reaction. Okay, more than 60. Okay. Okay, we look at this reaction mechanism. Okay, so there is one cyclic voltammogram. Okay, the above voltammogram describes the irreversible reaction of A. Okay, there is one species A. Peak 1 indicates the reduction of A to B. Okay, so A to B, this one. Peak 1 represent reduction. This is cathodic. Cathodic potential. This is using US convention. So, indicate the reduction. So this one, current positive, E negative. So this is reduction. This way, reduction process reaction on the working electrode. So there is the increase of current starting here. This is okay. It's start here. So then they increase because there are more ion of species A reduced to B. Okay. Then this is the switching potential. Okay, the system set to reverse back. Okay. So only a small portion of B oxidized to A. These two only a small B amount of B back to A. This is A to B here. Reduce to B, then you ask B to reduce oxidize back to A only small, about probably 20% back to A, but 80% probably change to new product, intermediate. Okay, so on the reverse scan, only small quantity of B oxidized to A here at 2, peak 2. Further scan on the positive, this is positive direction. Okay, further scan to positive direction, a balance of B, or B already changed to new product, intermediate, react, okay, B here, there is no reaction, but B react with solvent, for example, Z, okay, Z, it will produce C. So this is no involve electron transfer. So there is no current. Okay, if there is current increase upward or downward, there is involved electrochemical reaction. But when there is no current but something happen, for example, B, product B balance 80%, react with solvent Z will produce new product, but there is no current shown here, increase of current. So this is called chemical reaction. Chemical reaction involved. There is no electron transfer. If electron transfer involved, we call it electrochemical. Okay, for this current, downward or upward, so this show the increase of current, there's something happen here, so that the process is electrochemical reaction occur. But there is no reaction occur, but chemical reaction occur. There is no electrochemical reaction occur because when you scan further up, okay, there is one peak appear at 3. Okay, so this is new product C, chemical for just form, will oxidize to D, C to D, and then on the reverse back, the amount I, the height of IPC, this is IPC, and IPA here, similar. Ratio is 1. This is reversible. D back to C. Okay, peak 3, C oxidized to D. Peak 4, D already formed here, oxidized to D. D back reduced to C. But the amount of C form and D form are equal. Okay, they are equal, so they are reversible. Here is reversible between C and D, reversible. But here, B, A and B is irreversible. I hope you understand. But whenever you see the increase of current, there is involved electron transfer. So electron transfer involved or electrochemical reaction involved, pick one and two, involve electron transfer. So this is called E. For here, to form a new product C, there is no involved electron transfer. Pick 2 and 3. From 2 to 3, there is no electron transfer, so that is called C, chemical reaction between B and solvent. Then 3 and 4, pick 3 and 4 is reversible. It involves electron transfer. So this mechanism is called ECE mechanism. Okay, because it involves electrochemical reaction here between A and B. Then C, chemical reaction at the middle, B and Z, the solvent, and again E and C, C and D. There is current increase both sides, that is called electrochemical reaction. So this mechanism is called ECE mechanism. Electrochemical reaction plus chemical reaction plus electrochemical reaction. That is called ECE mechanism. Okay, so I hope you understand. I explained about this. C undergoes oxidation to P. D produce peak 3, okay, through electron transfer. This is E. Okay, on the reverse scan, negative scan, on the second clip, peak 4 appears. Okay, this is the conversion of D to C. The amount of C back to D, D back to C are similar. So that is reversible. So the process A to B is E, involve electron transfer or electrochemical reaction. So B react, the balance B react with the solvent or the C, that is chemical reaction, we call it C. Then C convert to D involve electron transfer because there is current involved, so it's E, ECE.